Hi, this is Dylan Pitt with a video explaining Ohm's Law for Eng 104. The galvanic chain mathematically processed was a scientific book published in 1827 by the German mathematician and physicist George Simon Ohm, which contained his complete theory of electricity. Within the book, the now widespread Ohm's Law was stated. Ohm's Law states that V equals IR, where V is the total voltage, I is the total current, and R is the total resistance of the circuit. Ohm's law was derived by an observation supported by empirical data and thus was not mathematically derived. To truly understand Ohm's law, the variables must be understood. Firstly, current is the amount of charged carriers that flow past a point per time interval, i.e., number of electrons per second, and is measured in amps, that is, coulombs per second. A fair analogy would be to compare the flow of electrons to the flow of water in a river, as the two examples do. Voltage is the potential difference of charge between 2 points in an electrical circuit, and can be described as the amount of energy required to move one charge. It is measured in volts, joules per coulomb. Referring to the water analogy previously stated, if the current is the flow of water per second past a point, then the voltage would be the gradient of the hill the water is flowing down. That is, the larger the voltage, or the steeper the gradient, the more of the substance that passes that point in the time interval, as displayed by the animation at the bottom of the screen. Lastly, resistance is an object's tendency to resist the flow of charge trying to pass it, and is measured in the units defined as ohms, which is in turn defined as the requirement of the application of 1 volt to move 1 amp past the object. Keeping with the river analogy, the ohmic resistance would be a section of river where the walls of the riverbed are closer together, thus reducing the effectiveness of moving the same amount of substance at the same rate achieved before, i.e. reducing the electrical current in the circuit. This analogy is shown at the bottom of the slide. Though the analogy is a good way to describe the different components of Ohm's law, the results of the analogy are not as simple as the results of the real-world applications of Ohm's law. For instance, powering a light bulb, not only would the current decrease, but also excess energy in the form of heat would be given off by the power formula P equals VR. Therefore, the creation of circuits out of the theoretical world must factor in not only the heat generated but also the effect of the heat on the resistance of the wires and resistor. Thank you for watching.